Yeah, can you hear me now, Phiala?
Sort of. You're cutting in and out a bit, but that was also the case yesterday that you're actually cutting in and out a bit.
Cutting in and out. Okay. I can try the other mic and see if it's any different. All right, I'm on the other mic now. We have handheld mics. You can see me holding it here maybe. So this is the room is not mic'd up, unfortunately. We have to pass these around.
Sounds good. I think there's some like background sound cancellation or something, because also yesterday when people were asking questions, occasionally it was cutting in and out. Not so bad that I couldn't understand what was being asked usually.
Okay. We'll see if there's anything we can do before we start, maybe. Background noise suppression, yeah. Let's turn that to low. All right, does this seem any better? So far, I guess I'll keep talking for a little bit and let's see. We turned the background noise suppression down to low.
Yeah, so far potentially that's better.
Okay, great.
We can run with it. It wasn't too bad yesterday anyway.
Mm-hmm. All right. Well, we're still people are coming back from lunch and everything, so we'll wait till 2 to actually start.
Sounds great.
Seems good on our end. All right, I think we're ready to get started when you are, Phiala.
Okay, great. So first, thank you for the great conversations in office hours just before, and also for the interesting questions over private messages in Slack. It's been really nice to be able to engage with you in a way that's not just through the lecture, which is a little hard to have informal conversations with. Okay, so where we left things last time is that we'd sort of set up calculations in lattice quantum field theory as something that you can do numerically, doing an integral over the gauge fields here as a very large but finite dimensional sampling problem. Essentially, we're going to sample over the space of gauge fields with a probability defined by this factor here. And then what we're left with is we have to compute whatever observable that we're interested in the matrix elements of the corresponding operator for. And we'd talked through all of this, and then we were starting to talk about different discretizations that you can write down. And we'd written down the sort of most naive fermion discretization, just doing, in this case, a symmetric finite difference. And we saw that the gauge links from the gauge fields come up here as parallel transporters that make this something that you can write down that's nice and gauge invariant. Okay, so I should warn you, for the first little bit of this lecture, we're going to go reasonably fast and occasionally a little bit loose because I want to get to the main points. And after seeing what we got through yesterday, I want to make sure we still have time for the main points. I have to cut some details in a few places. But the main point that I want to make here is that this is an example of why you have to be careful writing down discretizations of your action, whether gauge or fermion. This particular sort of naive way of discretizing the fermions has a peculiar continuum limit that's actually not what we'd like it to be. So one way of seeing why this continuum limit is peculiar is we can look at the Fourier transform, the inverse of the free two-point function, or of the fermion propagator. So if we do just a couple of manipulations, so let me just write down this Fourier transform here. Right, this thing we saw before, right? This just looks like our D. And for now, I'm going to simplify our lives just so we don't have to keep track of the gauge fields and set all the gauge fields to the identity for now. Okay. This D is, of course, this D is this free two-point function. Okay. So in fact, just by staring at this, you should already have an idea of at least one factor that's going to pop out of this. We should end up with a delta function in K and L, right? Just from momentum conservation, because we're doing the Fourier transforms for the psi and the psi bar separately here. So that should come out when we write down a few lines of simplification. But let me just rearrange this. Let me substitute in this here for D here. And I'm not doing anything deep with these manipulations. I'm just trying to get it into a form where it's easy to see that the continuum limit is a bit funny. So I've just substituted in this expression here. The size are pulled out here, right? So that's why here I have the delta functions n minus and mu hat and n plus mu hat. And just applying those delta functions, this now looks like something where you should be able to see we're going to get a delta function in K minus L. When we have an exponential of something minus the exponential of minus something, we can write that in a more compact way as a sign. And that takes me to the It's the form that I wanted this in. Where this d tilde okay. The point of all that manipulation was just to get this expression here so that I can write down the inverse of this again in a convenient form. And again, done nothing but substitute in so far. But let me write this down. Where all I've done to get from here to here, right? I want to write down the inverse of this, then I've multiplied both the top and the bottom by this. It simplifies simply, except you have to be careful with the gammas. The reason the gammas are gone here is that the anti-commutator of the Euclidean gammas is just g mu nu, right? So that's what happened in the denominator here. But and then if you want the position space guy, you can do a Fourier transform to go back again. But in this form, it's easy to eyeball this and see that when m equals 0, this thing is singular, right? At not just one point, as you would expect for a massless particle, but a number of other points as well. So looking at this expression, take m equals 0. This guy is singular at 0 momentum, as expected. But also at a number of other points. For example, 0, 0, 0, pi over a, or any combination where the pi over a's can be in any of the entries here, like pi over a, pi over a, pi over a, pi over a. And what's restricting the range of momenta that I'm writing down here, I'm just writing down all the momenta in the Brillouin zone. So that's the, if you like, the space of inequivalent momenta when we go into the conjugate lattice, or the reciprocal space, if you like. This is the space of inequivalent lattice momenta, which, okay, this guy here is from minus pi over a in each component up to pi over a in each component for all I. Okay, so what this means is that there's not one, but there are 16, or 2 to the d, so depending on what number of dimensions you're in, about which this is singular, so about which you have an approximately linear dispersion relation. And so it looks like you don't just have one fermion, which is what we thought we were going to have, but you have 16 fermions in the continuum limit here, which is not what we intended. So this is known as the doubling problem. So i.e. there are (16 points about which is an approximately linear dispersion relation. And we would say that another way, say that there are 15 fermion doublers, which were not what we not what we wanted to have. Okay, So you might have heard this referred to as the doubling problem. This doubling problem is very closely related to chiral symmetry, in fact. And there's a fairly straightforward way of seeing that I also want to sort of speed through. And to see that, we can start from here and we can take the naive continuum limit, so the limit as the lattice spacing here, A, goes to 0, near these various points, near these various singular points. And we're going to be able to see that you can relate all of them by unitary transformations. So if we just start from here, take the naive continuum limit, I'm going to Taylor expand this. Right. It's a little tricky that not a lot fits on the same board, but let me write it out again. So we're going to take this limit near any one of these singular points. And so I'm going to expand my momentum. Just do a Taylor expansion around this point. And what you see, we're just Taylor expanding the sign. So we're going to end up with a cosine here, right? This guy's just from the Taylor expansion. This here, given what these k mu a's are, remember they just have pi over a in any component. This thing here can only be plus or minus 1, and it depends on how many pi over a's there are in the different components, right? So this is just plus or minus 1. Depending on a, and remember we're just using a here to index all of the various points where we had that singularity. Okay, so this term only differs by a sign. And that makes it very easy to see that we can relate these different near zero energy regions by just unitary transformations. So we can write this another way. The only thing these SAs, which are our transformations, I'll write them down in a second, need to do is change the sign of that term there. Right, where these SAs, you can figure out explicitly what they could be. You just need a gamma and a gamma 5. And then when you think about commuting these guys through, because there's a gamma structure here, you can just change the sign of the second term to get the plus or minus 1 for each of the different singular points. Okay, now writing it like this, like I said, we've used a unitary transformation to relate all the different regions. You can see a relation between the doubling and the chiral symmetry. So if we think about a naive action for either a left or right-handed Weil fermion in the massless limit, we'll see that this relation tells us that the 16 doublers are going to look like 8 left-handed and 8 right-handed modes, no matter whether we thought we were writing down a left or right-handed mode to start with. So you think you're writing down one chirality, but you always get both. So this gives us a relation between doubling and chiral symmetry. So let's write down this guy again, but specify we're going to write down a left or right-handed Weil fermion. So that just means we need to put a projector in. Massless limit, that's why the m's have gone from up here, right? No m's, just talking about massless. And I'm going to put in a projector. So 1 plus or minus gamma 5 over 2, just our standard chiral projector. If I commute this through here, pick up an extra sign. Where this epsilon, I'm just using to stand in for the plus or minus sign. So epsilon A is +1 or -1, depending on the permutations. So there's 8 here and 8 here. And so what this is telling us is that whether or not whether we started with a plus or a minus here, whether we thought we had a left or a right-handed fermion, actually we have an equal number of left and right-handed modes. So we can't write down an action for a single chiral fermion. So the 16 doublers appear as 8 left-handed and 8 right-handed modes. So we failed to construct left and right-handed modes, no single chiral fermion. So this is an example of a more general statement, which is the Nielsen-Ninomiya theorem, which one version of that statement is saying that under certain very general assumptions, so if you have a fermion action where that's translationally invariant, that's local, that's Hermitian, you'll always have an equal number of left and right-handed modes. That's one way of saying it, so you can't have a single chiral fermion. Another way of saying it, and this is more general than just a Euclidean statement also, is that it is not possible to construct a lattice fermion action that's ultra-local, chirally symmetric, and undoubled with the right continuum limit. So this is one of the reasons fermions are tricky. So let me just write down a statement of this theorem. This is really the point that I'm trying to make here. We went through a little bit of the math so you can sort of see it come out from the naive fermion action, but this is the generic statement. And it's a pretty important theorem. It is not possible to construct a lattice fermion action that is ultra-local, or sometimes people don't say the ultra, chirally symmetric, undoubled, with the correct continuum limit. Okay. There are various proofs. Some of them are a bit involved, but for the sort of simplified Euclidean statement, it's actually not that hard to prove. You can basically just reduce this to the Poincare-Hopf theorem. So that's an interesting exercise if anyone feels like cranking out a page of mathematics. So if you want to do that, the idea is that you start with the locality part, right? Which tells you that the Fourier transform of essentially D has to be a continuous vector field on the Broughton zone. And the zeros of that continuous vector field correspond to different doublers. Then around each zero, the index of the vector field is ±1. So you have a saddle or a source of singularity. They're left and right-handed. And then you can just apply the Poincare-Hopf theorem which tells you that the sum of all those indices is the Euler characteristic of the manifold. And in this case, the Breuer zone is a 4 torus, so it has Euler characteristic 0, and so you need to have an equal number of plus and minus ones, which is an equal number of left and right-handed modes. So this actually follows fairly, a proof of this sort of simplified version follows fairly straightforwardly. You can do it in just a few lines. Okay, so this has consequences, right? It means that you have to get around the doubling problem somehow. The general idea is that you violate one of these assumptions in some way and hope or construct it such that that violation goes away in the continuum limit, right? And which one of the assumptions you violate, or how badly it's violated, or how badly the continuum limit is, that this is why knowing in advance about the physics of your problem, especially about any impact the symmetries might have, especially chiral symmetry, is really important, because it can influence what choice of action you make, which influences not just how expensive the calculation is, but how tough the continuum limit is to take, and so on. So various ways around the problem. And they have various consequences for chiral symmetry. But as I said, the general idea is you have to violate an assumption in a way that hopefully doesn't have terrible consequences. So we're not going to go in too much detail through various ways, but I will talk a little bit through some of them. So one is what's called Wilson fermions. And because these things are all easy to look up and to save some time, I'm not going to write out too much detail about them. But the idea of Wilson fermions is essentially that you break chiral symmetry, that's the one you give up, explicitly. So even when m equals 0, by adding an extra term, you add a second derivative term that acts like a large mass of order of the cutoff at the doubler poles. But so it's irrelevant at 0 momentum. And so what you're really doing is driving all the doublers to higher energies with an extra term. And that extra term you write down, you make it so that it vanishes as a goes to 0. So it vanishes in the continuum limit. So you're not doing any damage, but you've moved all the doublers out of the energy region that you're interested in. So this does lead to discretization errors of order the lattice spacing A. And then there's various things called like semantic improvement programs where you add even more terms to try to cancel out the leading discretization effects. But this really breaks chiral symmetry. For a lot of problems, chiral symmetry is not that important though. So this is a very useful fermion action in many cases. And you add a term to drive the doublers to higher energies, essentially. Okay, another very useful option is what's called staggered fermions. And we could have entire lecture series about any of these. The idea of staggered fermions is sort of what it sounds like, is you stagger the lattice. So you make odd and even sites. You distribute the 4 components of the Dirac spinner to different sites. A consequence of that is you end up with 4 different species, also known as tastes. And then you break taste symmetry. So it's sort of a different way around the problem. You end up with sort of, again, differences between odd and even sites, which has its own consequences. There are attempts to basically preserve some version of chiral symmetry. So in particular, we could talk about Ginzburg-Wilson fermions. So the general idea there is you preserve what's called the Ginzburg-Wilson relation, which is a lattice version of chiral symmetry that reduces to the usual symmetry in the chiral limit. So this is preserve some lattice chiral symmetry. Or the Ginzburg-Wilson relation. And there are various examples of this with names like there's overlap fermions, there's domain wall fermions, there are things called perfect actions or fixed point fermions. And in some ways, these are the nicest because you really do have some version of chiral symmetry left over, but they're computationally more expensive. And so the moral of this is really that which fermion action is best depends on the application. It depends on requirements of the problem, the physics of the problem, and there's lots of choices here. So not all lattice calculations of the same quantity will be the same, even in terms of the type of discretization artifacts they have, even just right from the beginning, from what kind of fermion discretization is used. So these are computationally more expensive. And the real upshot is that which is best depend on the application. And some of the big consequences, as we sort of discussed, are how well chiral symmetry is preserved and what the continuum limit looks like, how bad the discretization artifacts are as you take the lattice spacing small. Okay, so this is what I wanted to say about fermion discretizations. I also want to talk very briefly about discretizing the gauge action also, but if someone has pressing questions about the fermion discretization, now is a good time while I clear my board here.
Yeah, we have a question here.
Hi, this is Rebecca from Daisy. So I just wondered, is it obvious which choice is the best one, or do you just like, I don't know, like try multiple things and then find it out?
In some applications, it's obvious, like if you know you're studying something where chiral symmetry is really important, then you would want to start with one of the actions that preserves a lattice chiral symmetry. But in general, no, it's not really. What's best is sort of a complicated equation. It also depends on what sort of precision you need. So whether you can go for a computationally more expensive action, whether you know it's not particularly affected by chiral symmetry, so then you can get better statistics using Wilson fermions. It's a complicated question. For most, high precision calculations, multiple groups have done them with multiple different actions, and then you get agreement in the end, which gives you a lot of confidence that everyone's taking the continuum limit nicely and you really have controlled results. So that's sort of the ideal, that you make multiple choices and see that they agree and that none of the systematics are important.
Okay, thanks.
Okay. I have another question about the matrix S that is used in the Taylor expansion of the fermion. What is the subscript A for? I don't remember it seems like it's some function of what other particles are in the wave function, but that's not an argument to the 2-point function. So like, what is A exactly?
Yeah, so A here, I was just using to index these guys. So if there is just one pi over A in here, I would call that, A as 1. This I would call A as 1, 2, 3, 4, because there's pi over A in each of the 4 components. So it's just indexing all the different points where this guy is singular. And so then when we went here, I'm saying we want to take the continuum limit near each of these. So A is just indexing each of those momentum points where this guy is singular. And that same subscript popped up here, because if I want to relate all of them for all of the different Ks, we need to do a different unitary transformation depending on what that momentum was. So A is again just indexing which of those momenta it was.
Okay.
Yeah, I did go quite quickly through that. Apologies.
Any more questions at this point? Yeah, we'll see another one.
Hi, my name is Evan. I'm from Yale University. For QCD, chiral symmetry should automatically be broken by the explicit quark masses. And so would this automatically get you around the doubling problem that you mentioned?
No, no, it doesn't. I mean, so for example, for Wilson fermions, when we're getting around it, we're breaking chiral symmetry even when m equals 0, right? So this was all looking at even in the m equals 0 case.
More questions?
But that is why sometimes approximate chiral symmetry is good enough, right? Or even less approximate chiral symmetry is good enough.
All right, I don't see any more hands. I think we're happy for now.
Yeah. Or maybe a better way of answering your questions. You still want something that has the right limit as m goes to 0, right? And we don't have that here. Okay. Good. So for the gauge action, we also need to discretize it. This luckily is not quite as fraught as the fermion part of the action. And in particular, you can use closed paths of gauge lengths, so also called Wilson loops, to construct any gauge invariant quantity involving only gauge fields. And so we can use these types of closed paths of gauge lengths, Wilson loops, to write down our action. Then it's just a question of what combination we use that has the right continuum limit and discretization artifacts that are not too bad. And just like for fermions, ideally, the precise construction of the gauge actions are relevant as long as you have the right continuum limit. And the difference is really how bad the discretization artifacts are. So some will be better than others. So closed paths of gauge lengths or Wilson loops can be used to construct all gauge invariant. Whoa, apologies. How do I fix that? Gauge invariant quantities involving only gauge fields. And if we want to do the simplest thing, we can think about writing down a gauge action using only the simplest Wilson loop, so the 1-by-1 plaquette. So the simplest closed loop is the 1-by-1 loop, also called the plaquette. Right, and so by that I mean we're going to take a product of gauge lengths from some site n around a closed loop. And this has some directions, right? Nu and nu, so it has indices here. And starting from the site n, this just looks like real trace of a product of the 4 Wilson lines or gauge lengths that I just wrote down. Okay, well, the daggers here, they just change the direction of the arrow on the Wilson lines, right?
I had a question.
Yeah.
So I noticed you put a trace in there. what is the trace over? Is it of the space-time indices or the spinner indices?
We're doing a color
And
trace, yeah.
Trace, a color trace?
Yeah.
Oh,
Yeah,
okay.
so if we think about these objects again, even if we just go back here for a moment. So this thing here is really a matrix in space-time, in color, and in the Dirac indices, right? So these mu's are really carrying Dirac indices alpha betas. The u's are really carrying color indices A and B as well, right? So it's really the color indices on these guys.
Okay, or could we also define P mu nu with color indices instead of using a trace?
Oh, you could if you liked. Yeah, you could write out using a summation convention instead of writing the trace there.
Okay.
Yeah. Okay, thanks. And thanks for interrupting with a question. Better to answer now than when I stop and ask. Okay, so from here, okay, this is a closed loop. This is a nice gauge invariant object. What I really want is something like, f mu nu squared for my gauge action. And if you Taylor expand this, if you Taylor expand sort of this path ordered expression for u in terms of A, we can then know, we know what f mu nu looks like in terms of A. We know what these look like in terms of A. And if you Taylor expand this whole thing, you can identify how this relates to f mu nu. So I'm going to leave that an exercise, but I'll write down what the Taylor expansion gives you. And it's really expanding the u's, remember. In terms of our usual gauge fields A mu, in terms of which we know how to write down the action that we're interested in. And if you do that, you should see that you actually get the trace of f squared coming out sort of immediately in that Taylor expansion. And of course, you have corrections at higher orders that look like things like g squared, a to the 4, g4a squared, etc. So this is a couple of lines plugging in the expansion for each of these pieces and just simplifying out. But this then gives us a very convenient way of writing. This is called the Wilson gauge action in terms of just the simplest closed Wilson loop in terms of this plaquette object. So the Wilson gauge action right, and I'm trying to isolate this part. So I just need to subtract off the 1 and get rid of these coefficients, right? And this thing here has a limit as a goes to 0. Of just the trace of f squared that we were trying to write down. Okay, so unlike the fermions, you write down the most naive thing and there's no immediate crisis to solve. It does have sort of fairly bad discretization artifacts by some measure. So there are lots of ways you can try to improve this. And the idea essentially is that you can write down and do the same sort of Taylor expansion thing for different shapes of loops. Like instead of the 1 by 1, you could have a 1 by 2. You can Taylor expand it, and you can add this to the action with a coefficient that's just right to cancel out the leading discretization artifacts from the simplest thing you can do. And so, you can compute add more and more loops to the action, cancel out more and more of the leading terms, and that's called improving the action up to some order, right? So you could have an order A to the something improved action, and that's all that means. So you can improve the gauge action by adding additional loops. So e.g. 1x2 rectangles with the coefficients tuned to remove the leading discretization artifacts. Okay, and so then you want to imagine this in the context of sort of a bigger pipeline of a lattice calculation where the calculation is done at various different lattice spacings. Of course, this will affect what the form of your extrapolation to the continuum limit looks like, what sort of functional form you fit to those various data points to take that limit. Okay, so now we have a total action. We have a total lattice action. Which will look like a gauge part plus some fermion part. And there's some choice that's been made for each piece. Okay, so I just want to very quickly check in about symmetries. So our gauge symmetry, that's preserved by the lattice action, right? Our Lorentz symmetry is not. It's broken down if you have a hypercubic lattice to the hypercubic group, and that can induce various operator mixings under a normalization that are not otherwise there. So this is something you have to think about. I'm not sure we'll get a lot of chance to talk about renormalization, but the sort of broad idea is that because you've broken down the symmetry group, you now care about what irreducible representations of the hypercubic group things live in. And if you have multiple operators of different dimensions, but living in the same irreducible representation of the hypercubic group, they can all mix under a normalization, even if they wouldn't if you had Lorentz symmetry preserved. That gets particularly nasty if you have mixing with a lower dimensional operator, because that mixing can be power divergent in the lattice spacing, which means that as you make the lattice spacing small, the contamination from things you don't care about gets bigger and bigger and bigger. So you really have to think carefully about how to choose your operators in irreducible representations of the hypercubic group that don't mix with anything lower dimensional. So this is something to think about. And in some cases, if you can't find an operator that gives you the physical quantity you're interested in, that does not have divergent mixings, it can make it intractable to calculate. And chiral symmetry, well, this depends on the action you choose. Okay, so this is what I wanted to say about discretizing the action. And the main takeaways that I really wanted to give you there are more or less this, that you have to think about Lorentz symmetry and chiral symmetry, and that there's choices in each piece of the action. And those choices have consequences for how well the symmetries are preserved and also of the discretization artifacts. Any questions at this point?
Yeah, we have a few.
the mic was off. I apologize.
Okay.
This is Austin from University of Oregon. My question I will repeat is is there a fundamental obstacle to working with individual vial fermions and coupling them to chiral gauge groups like what we have in the electroweak sector?
Fundamental obstacle? Not really. I mean,
is there a practical obstacle?
I don't think so. I mean, if you're in a situation where the Nielsen-Neumeier theorem doesn't prevent you from getting what you want, if the, you know, for example, also if you had a theory where you happened to want all of those 16 doublers and that's the right continuum limit, then life can be good, right?
I mean, I think in principle, the problem you have is that because of the doubling mechanism, as you mentioned, you'll end up with both left and right-handed modes. So if you try to couple it purely chiral gauge theory, you sort of end up stuck with a vector gauge theory. Or if you use one of the other mechanisms, you end up breaking the gauge symmetry.
But if you want both, you're all good, right? So I thought that was maybe I misinterpreted the question. But if you want both modes,
right. I mean, yeah. Let's say I only want to couple to left-handed, right? Then is it just that, you know, the doubling mechanism automatically introduces the right-handed, and so I'm stuck with it?
Yes. If you only want left-handed, you're going to end up with an equal number of left and right-handed, and you need to use one of the other mechanisms to try to get rid of it.
Okay. Thanks.
But if you want both, you're okay.
Hi, this is Recop from MIT. So can you get like in this gauge action, like really funny gauge configurations that are topological and give you like monopoles or something?
Yeah. There's all sorts of interesting ways topology can come in. It depends on the theory. There's actually some interesting work trying to use machine learning to identify interesting topological features of gauge field configurations. Nothing, you know, super revolutionary that I've seen so far on that front, but yeah, you can do various things. You can take your ensemble of gauge fields and then you can try, you know, smearing them out, cooling them to try to see if you can identify instantons or various topological features. There was some interesting work, you know, quite a long time ago now, maybe 10, 15 years, where people like did damage to the gauge fields by trying to remove center vortices and see, well, if you have vortex removed configurations and configurations with vortices in, how different is the physics? Can you connect that to chiral symmetry somehow? So yeah.
Okay.
Over here.
Hi, I'm Arindam from Harvard. I had a question on the lattice action improvement. So you said that you have to tune some of these A4 or A6 coefficients for each observable. Is it like universal, or should I think of this as like some Wilson coefficient times irrelevant operators that I have to add in to remove power law divergences in the observables that you're computing?
No, you should think about this as a universal improvement of the action. So you should think, if you, instead of having the plaquette here, right, if you do the same expansion for some other loop, if we wrote out these terms explicitly, what you're trying to do is you're trying to take the next loop and put a coefficient. So in this action, we're going to add some other term, like say a rectangle term, but with some coefficient in front of it, so that the addition of this cancels the leading order discretization effects here. So this is really the discretization effects here in this action. What order the corrections? This isn't an A goes to 0 limit. It looks like this, but what order do the corrections come in?
I see. That helps. Thanks.
Any more questions? All right, I think we're good for now.
Okay. Great. So at this point, I think it's helpful to talk through like a very simple observable and see how the calculation goes and what it looks like. So observables. Okay, so what we can compute are Euclidean endpoint correlation functions. And so you have to relate whatever the physics of interest is to some matrix element of a local or non-local operator in some limit potentially. But let's look at a very simple observable like the mass of the pion. Which we can get from a 2-point correlation function. Okay, so let's look at two equivalent expressions for a hadron 2-point correlation function. Okay, so I'm going to call this thing C pi because it's going to be a pion 2-point correlation function. And I'm going to define this as this 2-point correlator here. Where this operator O pi which can be a function of u psi bar, is what we call an interpolating operator. And what I really mean is that it has the quantum numbers of the state that we're trying to study here. So for the pion, this could be, we have a pseudoscalar, right? Probably exactly what you would expect if I told you I was trying to write down a hadronic correlation function for a pion. We have a U bar and a D, and because we're pseudoscalar, we're going to throw a gamma 5 in. So this is the simplest thing I can write down, right? I'm going to say I want to create the state at 0, 0 and annihilate it at xt, and this is my 2-point correlator. Okay, this is obviously the simplest thing. You could also say smear out these quark fields, so have some function multiplying them that's summing over different sites. You can add additional gammas, anything as long as it has the right quantum numbers is fine. Okay, so let's write down two equivalent expressions for this. And one of them basically tells us how to do the lattice calculation and the other tells us how to interpret it. So it's this C pi. I could write down this expression as a trace in Hilbert space or a transfer matrix picture, if you like. Or I could write it down as a path integral. These are O pi's. I know my pi's look a lot like H's. This is just our interpolating operators. Okay, so one here, this is a trace in Hilbert space. And 2 here is a path integral. And so far I've done nothing. I've just written down two equivalent expressions for this 2-point correlation function. Okay. If we start from 1 here, we can rearrange to see what the Euclidean time dependence of this correlation function should be, and how it's related to what we might care about, which in this case, I said we want to calculate the mass of the pion. So So just rearranging this expression can tell us that. It can tell us if we calculate this, well, how is it related to the mass of the pion that we're trying to get? And this, if we simplify that in a moment, that will tell us, well, how do we actually compute it by connecting quark propagators in a lattice calculation. So starting from 1, we can rearrange to solve for the t dependence. Okay, I'm just writing this down again because I'm about to scroll the previous version off the board. Okay, this is a trace in Hilbert space. I can write it as a sum over all states in the Hilbert space, right? I can write this as just summing over all states. We can also, if we like, insert a complete set of states in here, in the middle. Capital T here is the time extent of the lattice, right? And now, well, I can get these Hamiltonians out of here, right? I can act on these states that we've inserted and pull out a tower of energies of those states. Okay, and so now, well, I hope you can already see sort of where we're going. This coefficient here, which is the Euclidean time dependence of this correlation function, contains all of the information we want. It contains not just, in principle, not just the energy of the ground state, the pion that we're interested in, but the energies of everything in this tower of states, which have the same quantum numbers as our operators here. So we can do a similar thing for Z, right? So Z we can also write as a sum. And then if we think about the limit as this capital T, so the time extent of the lattice becomes large, then only rho equals 0 contributes, for example, here. So let's take that limit first. So if we make the volume large, where this delta, I'm writing delta E sigma is equal to E sigma minus E0, and E0 is our vacuum energy. Okay, so how to get this? This is just literally saying only rho equals 0 contributes in the limit as t becomes large, and dividing out and being a bit careful with the higher orders in the expansion, this guy and this guy, right? Okay, typically you would project a correlation function like this to 0 momentum if we're looking for the pion at rest, just by taking the sum over all sites x, right? It's essentially just doing a Fourier transform there. So and so what we get is just something with just one index here, just a Euclidean time dependence of this correlation function. And this is the sum over all states with momentum 0. Some number, we'll call these guys Z, just some overlap factor, it doesn't matter what it is. And since we're at 0 momentum, we will now write these as masses. The exponential now has the mass of each state in that tower. So if we go and compute this 2-point correlation function, it depends on the energies of all states for which there's a non-zero overlap between the operator and the state. So those that can be created from the vacuum by this creation operator, every one of those states will contribute. So in general, a creation operator that you write down will create a state that's a linear combination of all possible eigenstates of the Hamiltonian that have the same quantum numbers. So for the pion, that would be the pion, but also excitations of the pion, 3 pions in a j equals 0 state, and so on. And a particular operator may have more or less strong overlap onto those different states. But in general, you'll just have this functional form here where this correlator that you can compute looks like a sum of decaying exponentials, where the exponents correspond to the spectrum of states with those quantum numbers. So this is how we'll analyze the data. Once we've computed the 2-point correlation function from Lattice QCD, we'll need to fit to this sort of a functional form to extract this, which is the information we're interested in. Starting from the path integral picture, we see how to actually do the computation. So that's the bit I'll do next. And any questions about this before I start from the other definition?
Questions? Yeah, I see one.
For the pion operator, does it ever make sense to have the, say, the U and D be spatially separated if they have, say, a pion wave function?
Yeah, so it would be more, you can certainly have operators with some spatial separation. For a pion, a more typical thing would be to smear out, where did I put the operator here? Would be to smear out both of these quark fields in some way. So you could write down some smearing function, if you like. So you could write down some Q tilde that looks like this, that looks like a weighted sum of the quark field at different sites to smear it out. And that's what you would typically do. You could also separate them spatially if you wanted. You'd have to still make sure you write down something that has appropriate transformation properties, to put in gauge links.
Okay.
Any more questions? Right, I don't see any. You have about 10 minutes left, by the way, Phiala.
Okay, great. Okay, so starting from the path integral picture, I'll just call this a U. This is what we have, right? And from what we saw before, we saw that we want to contract these quark fields. So these Ds, having written this on 2 lines makes it hard to draw my contractions, right? So the Ds with each other and the U's with each other, which we convert into quark propagators, right? You do all possible contractions for the pion, that's very easy, we just have this one. And then we know that we can write this as an integral over our gauge fields. We can do the fermion integral exactly, which gives us determinants. In this case, we have one for U and one for D. We still have e to the minus S for the gauge part of the action. And as we saw last time, we can contract all of the quark fields. We'll have one for U, contracting between X and 0. The gamma 5s stay there, they don't go anywhere. We'll have one for D from 0 to X. And so these are just the quark propagators that we convert by, that we compute by matrix inversion, essentially. This, if you remember, is sitting inside the probability distribution when we sample this guy. So another way of saying this is that we just compute this on each of the gauge fields that we've sampled on. So we can say that how you actually compute this is you're going to average over your configurations. And then you're going to having on each of those configurations computed a quark propagator. You have these large objects computed on each configuration. And you just compute the trace. And then you sum over all the positions X to get back to the momentum projected guy. So typically, I mean, this thing here with the propagators, you'll draw what's called a skeleton diagram, right? To see what's going on here. Here we have some point at X, some point at 0. We have an up propagator here going from X to 0 and a down propagator going from 0 to X. So it looks just like we'd expect for a pion. Okay, so this is the picture. We compute this numerically, and then you want to in some way fit it to this functional form to get out the information that you're really interested in this case, the mass of the pion. So if we are a little bit concrete about that, so having computed C pi, you do a numerical or statistical fit to, if we're really explicit, it looks like some number times e to the minus m naught t, where that's the mass we're interested in, plus some other number times the decaying exponential with the next state, and so on. And so what you will usually see people plot is what's called an effective mass, which is a nice way of visualizing these types of 2-point functions. If you just take the log of the ratio of the 2-point function and the shifted 2-point function, just from this expression here, you can see that these coefficients cancel out, the log's getting rid of the exponential, and this looks like the mass you're interested in plus some constant times an exponential decaying with an energy gap. So this is just some constant. This is some energy gap between the ground state and the first excited state. And so, of course, there's extra terms in that expansion, but if you see data for this effective mass, it will usually look something like this. right? And then the M0 will be this value that it's asymptoting to. This will be some sort of excited state contamination. Typically, you compute these errors with some sort of bootstrap or jackknife resampling procedure, but this really is just statistically, you've computed this on 1,000 configurations, then you have that distribution to make error bars out of for each point. This is here a Euclidean time t. The errors here, they grow. It's exponential with t. We'll come back to that later. That's sort of where some of the various intuition comes into and what gets hard about lattice QCD. If you have to go into very late times, it gets hard statistically. But this is essentially it. So the most naive thing is you say, okay, I'm going to fit a constant to this once it asymptotes. More sophisticated fits, you can do a fit to really multiple exponentials to the correlation function. So you're really fitting this time dependence. You have to be careful to take correlations into account. Of course, all of these points are correlated. But that's the general picture. You've probably already guessed, you could try to determine not just the ground state, but excited states here from multi-exponential fits. That's pretty hard just numerically. More typically, you would choose not just one interpolating operator, but a whole set with the same quantum numbers and form a matrix. And then they all have the same energies, but different overlap Z, right? So you can solve essentially a generalized eigenvalue problem to try to get out not just the ground state, but a whole tower of excited states. That's essentially how spectroscopy is done. Okay, if you have operators with more quark fields, the number of Wick contractions grows factorially, which is not a problem if you're interested in the proton. It becomes a problem if you're interested in doing nuclear physics. It grows really badly. So far, there have only been sort of proof of principle calculations of nuclear physics up to about atomic number 5 protons and neutrons, partly because the Wick contractions, that factorial is insurmountable very quickly. But this is the general picture, so I'm happy to take questions. I'm almost out of time, yeah, is that right?
Yeah, we're at 2 minutes left, so
okay, perfect. So I'll take questions, and then next time we're going to talk about more building intuition. So what's easy, what's hard, why, and I hope we will get to some of the phenomenology I wanted to get to as well.
Great. There are more questions before we break. Give everyone a moment to absorb things. Yeah, I see a question over there.
Hi, this is Sam again from Caltech. Can you give us an intuition why the error bars increase exponentially with time?
Yeah, we can go through this in more detail later. I mean, it's actually different from the pion than for other states. I was being sort of a little bit generic here, but for the proton, the simplest way of thinking about it is that you have a proton correlator, you have 3 quark lines, right? But the variance correlator, you can think about, the variance correlator, right, looks like this, right? And if you write down this guy, you'll have not 3 quark lines, but you have 6 quark lines. And you can rearrange that into, a proton and the antiproton, but also into 3 pions. And so then the variance correlator is actually going to decay with something that looks more like some Z factor with this as well as this. And since 3 pions is lighter than 2 nucleons, again, it depends on the parameters of your calculation. But so this is really dominant. And so then your signal to noise is going to go like something like an exponential with this in time from this difference between 2 nucleons and 3 pions. So it does depend on the states you're looking at, but in general, it's going to grow with time.
All right. Maybe one more question if we have one. All right. I don't see any more. So let's thank Phiala.
Thank you very much.
All right. So we have a coffee break here. And then this is the end of the official TASI events. I think there are student talks again following this. So once again, I'm inviting all the non-students to leave. But everyone can get some coffee first.